the solution to that is iterative methods. Okay, so there is an estimate of for 3D structured problem, the amount of work is kind of n to the 7, where the grids is O n to the cube, right? So it's to the 7. It's not to the 9th yet because there are some structure you can exploit, but for unstructured, it's close to O n to the 9th, where n is the number of grid points in each direction. Okay, so iterative method. So what's the idea? The idea really comes from the original meaning of these PDEs. Kind of the idea always comes from, a lot of times come from physics. So, for example, if you solve Poisson's equation, and it's, if you jump out of the mathematical aspect and look at where we usually need to solve these kind of problems, it's usually when we are considering a problem evolved over a very long time. So for example, we may actually be solving this problem, du dt equal to the second derivative of u plus f. And we are just looking at a problem either having evolved for a very, very long time, that du dt is approximately 0, or just the time scale of the problem. Let's multiply a tau here. It's so small that it achieves equilibrium almost immediately. All right, or maybe we are solving a vibrational problem, right? Plus a damping term is equal to this. And again, if the system oscillates for a very long time and eventually dies out, we get back to the Poisson's equation. All right, or even if you don't have the damping term, but like your boundary condition have some damping, it absorbs energy, ultimately all the kinetic energy goes away and you have a equilibrium system. So the first idea of actually that's kind of an idea that reoccurs in a lot of different places, is that if directly solving this problem is very expensive, is ridiculously expensive, why don't I just solve a time-dependent problem instead? And although the system looks actually more complicated, but maybe it'll end up being less expensive. All right, so that's kind of one of the original ideas of iterative method, is that I take a look at this system instead, and I use some kind of a very cheap, it doesn't have to be accurate type of time integration scheme like forward Euler, right? So what if I just do u of k plus 1th time step minus u kth time step divided by delta t is equal to if I do forward Euler, that's this evaluated at k, right, plus f. All right, and if I'm doing finite difference, for example, well, whatever I do, I ended up basically expressing finite difference, finite volume, finite element. I always kind of express this with a matrix A times UK plus a vector B, right? That's kind of the original, one of the original motivation of iterative methods, is that if A is very sparse, then multiplying the sparse matrix with a vector takes very little time compared to doing any fancy things like factorization with the matrix. Because to compute every entry of A times U, I just need to multiply the corresponding non-zero entries with the corresponding entries in U. I have to do nothing with the zero entries, as opposed to factorization where I actually have to do a lot of work, even if the matrix has a 0 entry. All right, I have to take the corresponding, I have to make sure the corresponding column of L and corresponding column of U actually multiply and gives me that 0, right? Okay, so A times U takes no time. So I can just keep iterating this until my UK plus 1 minus UK is almost 0, right? So if the system is stable and if I have enough damping, then ultimately after enough iterations, every time my U changes less. And eventually if my U almost never changes, which means my UK plus 1 minus UK is approximately 0, then I suddenly find out I have solved the system because my right hand side is equal to 0, and that's exactly what I want. I want to solve AU equal to minus B, right? Then that's it. So the iterative methods is basically saying that apply a formula. For example, in this case would be UK plus 1 is equal to UK plus delta T times A times UK plus delta TB. Okay, again and again, starting from essentially an arbitrary U0. So this is my initial guess. But in this case, if the system is stable, then whatever initial guess I start with is pretty much going to get me the same final solution, right? So the initial guess can be pretty bad. It doesn't matter. All right. It doesn't matter to the convergence. It matters to how many iterations it'll take to converge. So and then so let k equal to 1, 2, 3, etc. until a tolerance is achieved. For example, here my tolerance can be UK plus 1 minus UK divided by delta T is less than a certain epsilon. And in iterative methods, you can set epsilon to all the way from, if you don't care about accuracy, you can set epsilon to 10 to the minus 3, for example. If you do care, you may even set epsilon to 10 to the minus 12. Then, by taking U is equal to UK, I can declare that A times U, well, let me say the norm of this. A times U plus B, the norm of this is actually exactly equal to norm of what I enforce as a tolerance is less than epsilon. Or I can say I approximately have solved the system, right? So that's it. I can never, using iterative methods, it's rarely I can solve the equation to absolute precision. But like if it is sufficiently good to solve the system to some very high precision, doesn't have to be exact, iterative methods should be considered. All right. Okay. So, of course, this is a very primitive version of iterative methods. For example, how do you choose delta t, right? You should be choosing delta t to be as large as possible. So what should it be? The criterion, for example, can be stability. So we want to choose delta t to be as large as possible for stability reasons. And then you can also figure out that this delta t, this is kind of the critical insight in iterative method, is that this delta t does not have to be the same for every grid point. Why? Because I'm not interested in actually solving this PDE with absolute precision, right? I'm fine with taking delta t to be different for every different spatial grid point. Or equivalently, I can have this tau being a function of x, and no problem, as long as the system is stable, I'm going to be converging to the same steady state point. So it now gives us a lot of flexibility to tune what this delta t, or in this case tau times delta t, right? Tau times delta t, so that I can achieve as fast convergence as possible.